Alright, so let's say we have Earth, right? A certain mass of the Earth, and it itself has a distance to the center. We'll call that dE, center of the Earth. And I have a probe, I have a satellite here, right? I want to send that satellite to this new planet here. So if I send that there, I need to know how well it's going to work, which means I need to know how much it weighs on this new planet. Well, what's going to affect that? I need to know the mass of this planet. Let's say the mass of this planet is twice Earth's mass. So it's twice as massive as the Earth, and the distance to the center is actually twice the distance to the center of the Earth. Here's my question. How is the weight of this satellite going to change on this new planet? So let's say on Earth it weighed 3,600 newtons originally on the Earth. And let's see if we can figure out what it's going to weigh on this new planet. Alright, so we have the weight of the planet, the force due to gravity, is going to be equal to the gravitational constant times mass 1 and mass 2. That's the mass of the planet, in our case that's Earth. And mass 2, that would be the mass of the satellite, the probe. Alright, so this tells us that force is proportional to the mass, alright, and it's inversely proportional to the square of the distance. If you want to know why, stay tuned to the end of the video, but we're going to plow ahead anyway. This is the relationship we have. So, as far as Earth is concerned, all of this is 3,600 newtons on the Earth. So, for our new planet, it'll be a new weight, new force due to gravity. G doesn't change, a gravitational constant, but now it's twice the mass of the Earth. And the mass of the probe doesn't change, at least for our example it doesn't. And we have twice the distance to the center, and all of that is squared. So let's rearrange this a little bit. Let's pull this 2 out front, 2 times G, mass of the Earth, times M2, and I have 2 squared, which is 4, times dE squared. Now this, all of this, is the same as the equation I had before. All of that was 3,600 newtons. So really I have 2/4, and that's 1/2, times 3,600 newtons, right? And that's going to give me 1,800 newtons. So without knowing the mass of the satellite or the actual mass of the planet, I just know how they're related, I can figure out that new weight. And if you're curious about why and how we can do that, and why we can do that, stay tuned. So, if we look at, new sheet, let's say I take all the mass of that planet and I squish it down right there. That's the mass of the planet. Now I want to look at 3-dimensional space going out here. Alright? And imagine a square of area that's spread out about yay far. Alright? And there's that little square right there. Alright, we're going out in 3 dimensions from that point. Let's say that's a certain distance away. Right? The gravity is going to have a certain strength here because it encompasses that much space. Let's go twice as far away, twice the distance. Now I'm out here, so again I'm going to draw how much space I'm actually encompassing here. Now if I spread out twice as far, the area I'm covering is actually twice as wide and twice as tall. So this same square that I used here is going to be that same size here, but now I'm using 4 times as much area. So spreading out across 4 times the area. Let's see if we can keep this going. Let's go 3 times the distance, which is about approximately here. Set this up again. Now you guessed it, if I'm 3 times as far away, I'm spreading out 3 times as wide, I'm spreading out 3 times as tall, and now this same square, which is still this same size, is only, I have to cover 9 times as much area. So really the same amount of gravitational force, gravitational strength, has to spread out against full area, or 1/4 of the area, or 1/9 of the area. You could take a guess if I go all the way out to 4 times the distance, which is getting behind everything here, you'd imagine that this is going to spread out to 16 times the area, and you're only looking at 1/16 of the space, and 1/25th, and 1/36th, so on and so forth. So you can imagine with gravity spreading out this much, just like with light spreading out this much, just like with spray paint or a canister of air or something spreading out in 3 dimensions, you're spreading out over a larger and larger area, which is distance times distance. So if you spread out over a distance squared, you're going to get 1 over the distance squared for how much you have to spread out in each of these cases, the thickness, the strength, or the amount of light.